disasters are the most dramatic causes of soil erosion. Many tons of soil can be washed away and carried downstream. Trees and plants which hold the soil in place are torn up by wind and floodwater. We see vast areas of forest land destroyed by firestorms. Such devastation hits the headlines. Communities and governments jump into action to remediate the damage, and large sums are invested in preventing similar disasters occurring in high-risk areas. Less obvious and less dramatic is the natural erosion caused by the continuing effects of rainfall, wind, and the flow action of streams and rivers. Over time, it has created some spectacular formations. Natural erosion takes place gradually and insidiously. We may never control it entirely. Widespread and more rapidly damaging than natural erosion is the additional erosion caused by man. This is the accelerated erosion caused by earth-disturbing activities in agriculture, mining, logging, road building, and new home development. Construction work almost inevitably involves land clearing, which leaves the soil disturbed, stripped of vegetation, and therefore susceptible to erosion. It is accelerated erosion that is our greatest concern, as it depletes our life-depending soil. The U.S. Department of Agriculture Soil Conservation Service estimates that 3 to 4 billion tons of soil a year are lost from United States land through erosion. Of this total soil loss, 25 to 30% comes from non-agricultural sources. Although construction is not the largest contributor in terms of volume, the rate of runoff from construction sites can be the highest of all land-disturbing activities, and so can the rate of soil loss. Erosion on such a scale reduces the soil's ability to support vegetation, the source of food, oxygen, and building materials. It also threatens wildlife habitats and recreation areas. Sediment resulting from erosion provides a substrate for toxic chemicals, which are carried into water supplies. Sediment accelerates the siltation of waterways and navigable waters. Dredging these costs the U.S. Army Corps of Engineers about $500 million each year. The EPA estimates as much as $13 billion of taxpayers' money is spent on mitigating the off-site impacts of erosion every year. Not surprisingly, developers, cities, agencies, or other land-disturbing groups may now be faced with large costs to comply with tightening federal and state regulations. Obviously, it's preferable and more cost-effective to control erosion than to pay for its consequences. In this video, we shall look at the erosion process and then at established practices for its mitigation. Erosion occurs where soil particles are detached by the actions of water and wind. Eroded material is suspended in water as sediment and deposited through sedimentation. There are basically 6 types of water erosion: rain splash, sheet erosion, rill erosion, gully erosion, stream bank erosion, and mass wasting. Rain splash is the most important detaching agent. Raindrops striking a bare earth surface break up aggregates and dislodge soil particles. Sheet erosion occurs as runoff water moves across the surface of the ground, detaching a thin, uniform layer of soil. While often unnoticeable, sheet erosion is a common and very significant form of erosion. Excessive runoff and steepened topography may produce a network of small channels called rills. Research suggests that rill erosion accounts for the greater part of sediment carried down hillsides. But rills are ephemeral and can often be eliminated by good surface treatment. Left untreated, rills can develop into deeper channels, forming gullies. Tributaries and stream banks are particularly vulnerable to erosion, especially where the velocity of the flowing water is high and the resistance of the bank materials low. Landslides, mudslides, or mass wasting of shorelines, although less frequent, transport great quantities of sediment into water bodies. From rainfall splash through mass wasting, the amount of water velocity and energy increases. This means the methods used to control erosion are going to be more extensive and more expensive. Erosion is more easily controlled at the low energy types: rainfall, sheet, and rill. There are three mechanisms associated with wind erosion. Coarser grains roll along the surface in an action known as creep. At higher wind velocities, they bounce along the surface, saltation. Finer particles, silts for example, are picked up and resuspended in the air for longer periods of time. Methods to prevent soil erosion or reduce sedimentation are known as conservation practices or best management practices, often referred to as BMPs. Once erosion has occurred, sediment is produced. Temporary methods to control sediment include straw bale check dams, loose gravel or stone, gravel-filled bags, sand-filled bags, geotextile silt fences. Straw bales are one of the oldest practices for controlling sediment, but to be effective, they must be installed correctly and then be inspected and maintained. Bales should be trenched in place, placed on their edges, with the ties off the ground and staked with wooden stakes. Gravel inlet filters can be constructed using cinder blocks laid on their sides, with the open area covered by a screen. Gravel is then placed against the screen to let water pass through, while the sediment is retained. Burlap bags filled with gravel allow water to flow through and the sediment to settle out behind them. The loosely knit system of bag and gravel serves as a filter. On the other hand, geotextile bags filled with sand are effective in blocking the flow of water, but less effective in allowing the water to percolate through. Geotextile silt fences are designed to reduce soil sediment runoff. This one from Amoco is made of woven, inert polypropylene and is self-supported by wooden stakes. Water is allowed to filter through, while suspended sediment particles settle out behind the fabric, preventing soil movement from the site. Silt fences must be installed according to manufacturer's instructions to prevent sediment flowing underneath. This involves digging a trench, burying the bottom of the fabric in the trench, and backfilling it. For inlet protection, they may need reinforcement. More permanent structural methods of sediment control include check dams constructed from logs, rock, concrete, or gabions, all designed to reduce runoff velocities and trap sediment. Retention ponds hold stormwater and release it slowly. Detention ponds hold water for longer periods, allowing sediment to settle out. Catch basins are good practice on a construction site. As with all sediment-controlled BMPs, continued maintenance is necessary for their efficient operation. This means periodically removing and distributing or disposing of accumulated sediment. Keeping soil in its place and out of sedimentation devices is erosion control. And the simplest, most cost-effective measure to control erosion is to maintain a cover on the soil surface. The most effective way of accomplishing this is by establishing vegetation. Vegetation has three main functions: to intercept and reduce the energy of rainfall impact, to reduce runoff velocity, filter out sediment, and increase infiltration of water into the soil, and to hold soil in place with roots. Certain procedures should be followed, including the addition of fertilizer and soil amendments to promote vegetation establishment. These procedures should be based on the results of a soil test and related to the type of vegetation selected for long-term establishment. Sometimes the soil's limitation to grow vegetation is related to its structure. This is the case with soils underlain with impervious layers or hardpan, which restrict root development. Mechanical means, such as deep ripping, can be used to break up compaction, but at least one chemical method, Agri-SC from 4-Star Services, has been demonstrated which makes compacted soils friable and moisture in the soil more accessible to plants. This soil treatment is relatively inexpensive and can be applied by any conventional agricultural spray equipment. Soil bioengineering is the practice of using trees, shrubs, and other living plant material to structurally reinforce the soil. These need careful selection. If erosion is deep-seated, those with long roots will give greater support. If erosion is superficial, those with matted shallow roots will be preferred. When mature, the canopy can protect soil from rainfall, while the roots hold the soil fast. A traditional way of controlling shallow erosion is live staking. Typically, willow stakes cut from dormant plants grow well in moist soil, and some thrive on road fills or along gullies. Traditional wattling also makes use of available materials. Cigar-shaped bundles of quickly rooting live brush can be staked in shallow trenches cut at intervals on contour. Stakes can also be of live material. Biodegradable geotextiles can also be incorporated into the system, along with grasses and other plants. In soil bioengineering, materials may cost little, but it is skilled work and labor-intensive, and periodic inspection and maintenance are essential. Temporary erosion control measures are often necessary to protect the surface. These include emulsions for dust control, tackifiers and soil binders, hydraulic mulches, hydraulic matrices of composite materials, erosion control blankets, and geocomposite containment systems. Usually as a measure against wind erosion, organic byproducts or acrylic polymer soil stabilizers seal the surface or bind soil particles into aggregates. Wind-blown sediment can be a major violator of clean air laws. Coal dust from this storage pile is being treated with soil cement, a binder made of a blend of acrylic and polyvinyl acetate made by Midwest Industrial Supply. The binder produces a pliable surface resistant to wind action. Another application for soil cement is to control erosion and dust in desert areas. After the final grading and stabilization, rain will not destroy the grading along the firm surface so long as the soil sealant remains intact. Dust on unsurfaced roads, like this mine haul road, or helipads and airstrips, is not only a problem, but a safety hazard. Here we see road oil, a soil stabilizer from soil stabilization products, being used to provide a strong bonded surface. This is more economical than asphalt and more rapidly applied. Road oil is an emulsion made from modified natural resin, which is added to water and diluted according to application needs. A single coat sufficed to stabilize the helipad, but several coats were applied to the landing strip. Here we see a dyed liquid copolymer binder being sprayed to hold down the fly ash from the nearby liquid coal generating station. This product is Soil Master from Environmental Soil Systems. When it's mixed with water, it bonds with the ash particles to form a water-resistant membrane which stabilizes the surface against wind erosion. On quite a different site, this binder is used to prevent the sand from blowing onto the main highway. It was also used to stabilize the nearby dunes. With this device, the Soil Master stabilizer was sprayed on copper mine tailings. When diluted with water, binders can be used as tackifiers by themselves or with mulching. Hydraulic mulches can be made of recycled paper, wood fiber, cotton waste, or other biodegradable materials. This is an economical way of delivering seed, mulch, and fertilizer. Mulch also protects the surface from rainfall impact, increases moisture retention in the soil, and moderates soil temperature. In some erosion control projects, specifications call for a particular blend of materials. Hydraulic mulches, soil binders, and other amendments may be combined to produce a composite matrix, which is hydraulically applied with seed to provide a high level of protection. A typical example is the emergency erosion control effort following the Oakland, California firestorm. Here, a combination of recycled paper mulch, wood fiber mulch, acrylic copolymer, and seed was applied to over 500 acres of the burn area, with successful results. Another example of a hydraulic matrix used here on a landfill is Airtrol, natural U.S. gypsum plaster, which can be mixed with seed, fertilizer, and water to form a cementitious binder. This matrix provides a protective crust-like cover of about 1/4 of an inch, which controls water and wind-induced erosion and holds seed in place. The matrix retains moisture in the soil and lowers soil temperature. Applying seed, fertilizer, control emulsions, tackifiers, soil binders, hydraulic mulches, and matrices requires specialized hydraulic seeding machinery. Although the principles of application are simple, equipment has become quite sophisticated. GeoQuip's hydroseeder boasts quick-release camlock hose couplings as a precaution against clogging, and a built-in fresh water tank so the main tank can be flushed out on site. The driver can run the side hose through electronically controlled hydraulics. Looking through his rearview mirror, he can see the nozzle, aim it, and conduct the operation himself without getting out of the cab. Erosion control blankets are rollout devices, which can be placed in two categories. Blankets made of natural, biodegradable materials, and blankets made of synthetic, non-biodegradable materials. One of the oldest forms of erosion control blanket is of natural jute. Belton's GeoJute is an open weave fabric which allows light to enter and plants to grow through it. Like most blankets, jute is stapled to the ground with staples, pins, or wooden stakes. The blanket drapes to follow the land contours and lasts while the vegetation establishes itself before it degrades. The open weave allows hydroseeding to be applied after as well as before installation. Coir, woven coconut fiber, is another natural material used in the erosion control industry. We are looking at GeoCoir Decaway, again from Belton. It can be woven into different weights and meshes. Much tougher than jute, coconut fiber lasts from 4 to 10 years before it degrades. Coir can be used to support stream embankments and channels and to hold the seeds in place until the plants take over the support. Here, a high-strength coconut fiber geotextile from Bonterra, America, is used in the construction of a retaining wall which follows the bends in a stream. Using a plywood form, the wall is constructed in 18-inch lifts, extending 4 feet into the bank. Willow cuttings to be planted through the fabric will be well established by the time the product degrades. This Curlex blanket from American Excelsior, at work on a holding pond, is made of curled wood encased in a photodegradable plastic netting. The wood fibers control erosion and promote growth by holding the seed in place. In this application, the contractor made plantings through the material after installation. Installing erosion control blankets is a relatively fast and unskilled operation. These North American green straw blankets are being used to cover an embankment. While on this 80-foot slope, double-netted straw blankets have been installed to prevent erosion and sediment deposition on the railway lines below. Here, blankets laid on landfills have been revegetated to prevent underlying drainage systems and trash being exposed. In this application, erosion control blankets were used around a site of a new supermarket. 2 grades of Bonterra erosion control blankets were selected. A straw blanket was placed initially and then covered by a heavy woven coconut fiber geotextile. This was because the site was steep and exposed to frost shear and severe winter weather. The greening began with the arrival of spring and the wildflowers that were part of the specified seed mix. This blanket from North American green is not constructed of natural fiber. It is a synthetic flexible channel liner designed to remain as a protection against scour on the channel bottom. Laid over the seeded channel bed, the liner protects seeds and soil from being eroded by water flow. Once established, the roots remain entwined in the non-biodegradable mesh. On the shore of this dike, ripe barley has its roots anchored in Axos encamat, a 3-dimensional matting of heavy nylon monofilaments fused at their intersections. 8 months before, this matting was pegged down on badly eroded earth, seeded, and filled with friable topsoil. Encamat is a root reinforcement matting, which also resists the shear forces created by high-volume discharges. It is used to promote vegetative cover, to slow water flow, and control erosion in ditches and stormwater channels. It is also installed on embankments and other steep slopes for hydroseeding. Wherever greater stabilization is necessary, cellular geocontainment systems can be used. Seen here is Axos Armature, a 3-dimensional semi-rigid matrix made of non-woven polyester fabric. The cells can be filled with soil, sand, or aggregates according to the application. On this site in British Columbia, the cells are filled and planted with native spruce and pine trees. GeoWeb from Presto is a containment system made from welded polyethylene plastic strips. Again, sections are flexible for transportation and placement, but once filled, the 3-dimensional cells confine and reinforce the fill to form a structural composite. The cellular structure will conform to contours, but prevent flanking or movement of the infill. Cell walls allow normal drainage, but hold the infill material in place, forcing water to flow over the protective system to prevent erosion. For low water flow velocities, the infill can be of native soil, later vegetated to give natural cover. For medium flow velocities, in channels for instance, infill can be of crushed rock. When using geocomposite containment systems, most channel installations require a geotextile to be laid between the substrate and the composite. Where there is hydrostatic pressure, the geotextile directs the water to open cells that have been filled with gravel, allowing the water to drain into the channel. When concrete fill is required to protect severe slopes or channels with continuous flows, ready mix can be discharged directly into the cells. For stream bank stabilization, and in areas where erosion forces exceed the capabilities of vegetation to provide long-term protection, structural methods for erosion control are sometimes necessary. These include precast concrete revetments, formed concrete systems, and wire mesh baskets known as gabions. This example of an interlocking concrete revetment system is Trilock from American Excelsior. It can be left in its natural form or backfilled with soil and seeded. It can be installed without the use of heavy equipment and can therefore reach inaccessible areas or be used on smaller projects. Concrete block systems like Trilock are considered a more attractive alternative to traditional riprap. Interlocking blocks can be laid on stream banks in sensitive areas and on long, steep slope channels. When laid as a mat, they can allow for below-water applications. We're now looking at another articulated block system, Nickelon's Armorflex. Typically, this is used in moderate to severe open channel flow and wave conditions. It offers long-term structural protection as well as a vegetative surface, which acts to filter pollutants and minimize their discharge downstream. In a wave climate, the open cell blocks are backfilled with crushed gravel, overlying a base drainage medium. A modification of the use of concrete for bank protection is this concept of a fabric-formed concrete revetment system, which is placed over a filter fabric. This is an armorform system from Nickelon. 2 layers of woven synthetic fiber are formed into an envelope, which, when injected on site with a very fluid fine aggregate grout, sets to form a concrete mattress in minutes. Excess mixing water is expelled from the permeable fabric forms. Hydraulic uplift pressure may be relieved by inserting weep tubes at specified intervals. Once filled, the fabric has performed its function and is free to deteriorate. The concrete provides the erosion control. As Armorform's rough surface offers low resistance to flow, it is suited to steep gradient flows. Maccaferry gabions are flexible, permeable structures which are designed to adapt to considerable soil movements. They can be laid in dry conditions or underwater. Gabion blocks and mattresses are suited to highly eroded banks, while the thinner revetments of mattresses are typically used for protecting less steep lower banks and for foundation aprons to prevent undercutting. Soil and seeds may be introduced into the voids in the stone fill either during or after construction. Plants can be grown in the external steps of the gabion structure or cuttings planted so their roots gradually penetrate through to the soil beneath. Rocky faces covered by a rockfall netting can be hydraulically seeded. Alternatively, a biodegradable mat containing mulch and seed mix can be placed under the wire. As we've seen, measures to control erosion and sediment range from the simple and temporary to the more sophisticated and permanent. There are 6 basic criteria for evaluating the relative merits of a best management practice. Its environmental and institutional acceptance, the cost of material, installation, and maintenance, its erosion control effectiveness, its ease of installation, its ability to promote vegetation, and finally, its operational requirements such as maintenance. In selecting from appropriate alternatives, we also have to consider the current regulatory environment. So great is the concern about annual rates of soil loss and the sometimes disastrous effects of sedimentation that federal and state laws are putting increasing pressure on land-disturbing industries. Some states have taken a lead in providing positive guidelines, manuals for BMPs, and video instructions for their correct installation. If designers and engineers can incorporate appropriate technologies for erosion and sediment control into their planning, they'll be able to offer additional services to clients. Present and future regulations may actually present them with new opportunities, even new professional direction, in taking a lead in the environmental improvement business.